paper discussion, 1,000-layer networks for unsupervised reinforcement learning. This paper got Best Paper Award at NeurIPS this year. Kudos to Latent Space for doing a show about this and pointing it out. I should have probably been on top of this myself, but this year I was a little bit, I would say my performance with NeurIPS wasn't as much as I thought. But nevertheless, I think I'm able to kind of get the gist for what NeurIPS was all about this year, because we had Richard Sutton giving a keynote. We had a couple of papers that we discussed about things like vision language action models, and generally just models that deal with action and reinforcement learning inspired robotics models. And this one is probably the most important one, and it got Best Paper Award. So I think this year's NeurIPS is probably a good indication for where we're going with AI. We're going real world, we're going self-supervised reinforcement learning for agents. We're going more into finding your own way without no priors or very little priors, better lesson applied to the real world. And I think this paper is absolutely in line with that. So I think the most important thing about this paper is that it's not even really reinforcement learning anymore, because what they're really doing here is actually what's called classification learning. And I'm going to try to explain the paper. This is a technical paper, and I'm not a technical podcast. And also, I'm not technically that averse, but nevertheless, I think it's worth discussing some of the technical details here. And most importantly, the way this project has been designed from the get-go, it has been, the idea was to not tell the model what a reward is and when it's doing well and when it's not doing well. Which is, if you think about it, probably the most dramatic exclusion you can choose to do in a reinforcement learning network. I mean, reinforcement learning is all about rewards and goals. It's this idea, the stick and the carrot, like you tell your child you did well here, you didn't do well there. Now, what they are doing here is kind of like what David Deutsch calls take children seriously, which is you just let the model do and figure it out itself. So that's fundamentally what they're doing. Now, the question is, of course, how are they doing it? How does a model know when it's on the right path? How does it know it's making mistakes? If you don't have a reward function here, if you don't tell the model explicitly it's doing well or not doing well, then what exactly is it doing, right? And the way they're doing this is through classification. So what they're doing is they're saying we're looking at trajectories, lots and lots of trajectories. So think of it like a pre-trained model that looks at, for example, how you go through a maze, right? So imagine you have a simulation where you're going through a maze, and you do that millions and millions of times in different types of mazes. And the goal now is to develop an agent that can go through a maze on its own, completely new maze. There's no memorization, none of that stuff. And you're not telling the agent, you did well here, you should do this, you should do that. The agent figures it out itself. So how do they do it? Well, they look at the next state. They look at the state that they're in right now, and then they look at the next state, and they look at how does this state compare, like does this state fall in the class of states that have a high probability of getting me to the endpoint. So you're kind of looking like in all the millions of maze iterations that I've been exposed to in pre-training, typically a state like, let's say the state I'm seeing right now, I can classify it as a state that gets me to nowhere. So I need to change my state. And then I change my state and I do that again. So this is more of a, like, and the authors in the latent space interview talk about it. It's more like a vision model, right? Where you're classifying things, where you're comparing, like, does this look like that, or does this look like this? Is A similar to B, or is A similar to C? So that's the fundamental idea. But what I found so fascinating about this is really, think about it, like, imagine yourself, right? I mean, think about a typical example. Take your career, let's say my career as a hedge fund manager, and imagine I have a reward function to follow. In other words, I have I want to know when I'm doing well, and I want to know when I'm not doing well. And the way most people do this is they look at, let's say, what are other people doing? Who is making more money? Who has a bigger house? Who has the hotter wife? Like those kind of things, which is, that's how humans generally classify themselves. But I've been always saying that, actually. When you're in a hedge fund business, the one thing you should be looking at is, what's the end state here? And how does my current situation correspond to the desired end state? So, for example, the one thing in the hedge fund business that I think is incredibly important for some people, for me, for example, is longevity. Like, you want to stay in the game for a long time, because the longer you stay in the game, the more knowledge compounds, the more capital compounds, and the more you're going to make. Maybe in the first 10 years, you're not making as much. In the next 10 years, you might even not making as much, and then all of a sudden it compounds, you make a lot of money. So there's this end state, and then tracing back to where you are today. And this is very similar to what the authors are doing in this model. So they're looking at end states, and they're classifying. That's why it's a classification learning model. How does my current state correspond to the class of situations that have a high likelihood of getting me to the desired end state, or the goal? And goals are end states. So goals are states that end up in a situation that is desirable. That's a goal. So you got out of the maze, versus you got 10 million iterations in this particular maze, and you got 0.5% of those got you out. All the others didn't. So the 0.5% that got you out, those are the goals. And then how do you pursue them? There's different ways to pursue them, of course. And what the authors learned is two important things here. One is a model like this is scalable. In other words, it can be scaled with a deep neural net. You can have 1,000 layers, which is what the title says. Because generally in reinforcement learning, the layers are not that deep, because you have problems with gradients and the problem with the sparse reward function, which is kind of inherent in reinforcement learning. So sparse rewards are typically not good for deep reinforcement learning. If there is enough feedback, so if there's not, there's no sparse rewards, there's lots of rewards all the time throughout the lifetime of the learning space, then yeah, you can have a deeper neural net. But those are also the easier problems, and most reinforcement learning problems are not like that. They're much more like sparse reward type situations. So in those kinds of situations, like, for example, like I just said, in the situation of your, let's say, your own career, there's it's a very sparse reward function, because you have basically only one reward, which is at the end of your career, have you succeeded or not? So how can you use any kind of probabilistic models for something like that? Well, you can, because you might be able to just look and classify your current position with other positions that led to the end game that you want to achieve. So this goes also back to some of the, I don't know what I want to call it, wisdom maybe. So when people say, look, the best way to advance your own life or your own career is to to go backwards. Where do I want to be when I'm 80? Where do I want to be? Well, okay, if I want to be at X when I'm 80, where do I want to be when I'm 70? Where should I be when I'm 60? Where should I be when I'm 40, 30, 20, so forth. So it's kind of very similar. And I find these types of revelations always very fascinating. It's typical when you look at AI, when you actually work with AI, you always come to this type of conclusion that you learn a lot about life, and you learn a lot about how your own intelligence, for example, your own intelligence evolves not very dissimilar to artificial intelligence. So biological intelligence is not very dissimilar to artificial intelligence. The authors talk about batching. They talk about epoch pruning and things like that. That's for the technicians out there. The paper's attached in the show notes. But one of the things that you always want to pay attention to in any kind of deep neural net is the normalization and the batching, which means that like you don't want every piece of information always to influence the weights of your network. You kind of want to average it out a bit and batch it because again, you don't want one outlier information to sort of move a certain part of your network into a direction that is not desirable. You want to average it out, you want to normalize it, and you want to batch it. Maybe you don't want to do, if you have 10 million runs in a training, then I don't know if maybe 5 runs per batch is enough. Maybe you want to do 1,000 runs per batch, or maybe only 100. I mean, that's kind of what reinforcement learning researchers are doing. They're tinkering around with these types of things, and they're trying to figure out what is the best way to achieve the goal, which is of course the most optimal network that allows you to execute against the strategic prerogative. In this case, for example, to have a robot that can move through a maze, and in the future to have generalized robots that can learn from lots of generalizable data and also learn and get better with more compute and very little priors. I think it's a good example of how a paper that wins best paper in Europe's really has to be a little bit more than just an academic paper. I think it has to have an inspiration. It has to be a little bit of a risky bet, and I think that's what these authors did. And therefore, I think I applaud them for that. And it's one of the papers that I think will definitely have an impact on me and my research. And it's also in line with what Richard Sutton's talking about. And if you look at some of the history of the authors, they are certainly enamored with bitter lesson. So they're trying to find, but enamored with the bitter lesson, that's, honestly, who cares? And I find it also a little bit, almost ridiculous to deal with this question of well, I'm a bitter lesson pill person versus not. I mean, who cares? Like, if you think the bitter lesson has a chance to be sort of the underlying prerogative in AI, then work towards it. Find solutions to problems that are encountered in the bitter lesson, and that's exactly what these authors are doing. Thank you.